jump on the hand plate with. This is the art of engineering. I am the Lunatic Painter, and this is an episode, the inaugural episode of How Works. Today, we're going to look at how the humble diode does its thing. Now, this is a piece of wire. We all know what this is, and we can feed current through the wire via the conductive metal center, and we can protect ourselves from the voltages within because of the insulator on the outside. So here we have a combination of insulator and conductor working in concert to do the job that it's required to do, which is to carry current. The thing about this conductor, of course, is that I can feed electrons in this direction and I can feed electrons in this direction. The wire really doesn't care. But the diode is a magic conductor, and it's a magic conductor because it will allow current to flow one way but not the other. I always found this really fascinating as a young person, and I really wanted to get to the bottom of how it works. And I guess getting to the bottom of how that component works is really how the magic of electronics happens, because once you understand the diode, you can get an understanding of the transistor, and you're on your way to understanding how this fantastic modern Internet of Things world works. Now, diodes come in all sorts of shapes and sizes and all sorts of flavors. They all have the one thing in common, of course, and that is that they allow current to flow in one direction. Some of the diodes you may be familiar with are things like our LED. LED is an acronym for light emitting diode. So it is a diode. It needs to be correctly polarized, which means the positive needs to go to the correct lead and the negative needs to go to the correct lead. And if it's connected correctly, it lights up. We also have small signal diodes. That might be used as a detector in, say, an AM receiver. And of course, the diode we're going to be looking at today, a power diode. It's a 1N4004. And you'll probably notice that the thing that these diodes have in common usually also is that if they have a body, they'll have a stripe. And the stripe is telling you that that is the negative side. So the other side has to be the positive side. So it's a way of making sure that you put this in the correct way around if you want it to conduct. Enough of me babbling on here. Let's head over to the blackboard and let's do a little bit of a chalk and talk about how a diode works. And then please stick around because I will be showing you my brand new digital storage oscilloscope, and we will connect up a signal generator and we'll build a little breadboard circuit, and you'll get to see how this works in real life. So unlike some of those other videos where you might have seen someone showing you an animation, I will show you in real life how the circuit works. Let's go. Now, the first thing we need to know about a diode, of course, is that it is polarized. Like we said, it can only allow current to flow in one direction. That's what polarized means. So polarized is a word that you might want to get familiar with. Components that are polarized need to be put in the right way around. And your standard diode normally looks like this, and it normally has a stripe at one end. These are metallic leads that conduct current. This is where the semiconductor lives, and it's usually contained in a resin casing to make sure that it's insulated, to protect the silicon that's inside from the outside world. Now, the end with the stripe is termed the cathode, and it's designated with a K normally, and the other end is the anode. So we go anode, and that is the positive end, and we go cathode, and it's actually spelt with a C just to make things a little bit more confusing, and that is the negative end. In a circuit diagram or schematic diagram, there's a symbol that's used to represent our diode. And it usually looks something like this. So that is the schematic symbol. The anode is the arrow, the cathode is the line. So you can see that that's a nice way to remember which is the negative end, because stripe and stripe. Another thing to remember is quite often in electronics, we're dealing with what's known as conventional current. Some people say that's the electrons flowing in the opposite direction. I think it's an historical accident. I think when they were first playing with electricity, people thought it was a flow of positive charges, and that mistake has stuck till the present day. So for conventional current, we've got our positive end here, our negative end here. So our conventional current is going to flow in that direction. So if you just remember the arrow is pointing in the direction that the current flows and that it's conventional current, that's a nice way of remembering that. So our conventional current's flowing from left to right, and of course our electron flow, and I'm going to draw a little electron in here and give it a negative, is going to be flowing in the opposite direction. So let's do a quick recap. Diodes are polarized, which means they have to be put in the correct way around. They have an anode and a cathode end. Anode is positive, cathode is negative, and the actual schematic symbol here tells you the direction of conventional current because the arrow is pointing in that direction. So we've got our anode end at this end and our cathode end at this end. That's our diode. Now we're going to rub this out, and we're going to discuss how it actually stops current from flowing in one direction. Stick around. Now, earlier on in the video, we discussed our piece of wire. And in that discussion, we talked about the fact that the center, the metal part, is the conductor, which allows the free flow of electrons in either direction. And the outside is the insulator, which protects us from any high voltages and currents that are existing inside the conductor. But between substances that conduct and substances that insulate, there's a thing called the semiconductor. And semiconductor is what allows modern electronics to happen. One of those semiconductors is silicon. Germanium is another one. And as conductors go, in their pure state, they are pretty rubbish at conducting. And they're not perfect as insulators either, hence the name semiconductor. So like I was saying, if we take our silicon, which is a semiconductor, and it doesn't conduct or insulate that well, sort of lives in the nether regions between the two, but we take our pure silicon and we dope it. Okay, so this process we're talking about now is called doping. There's a whole list of doping substances that you can use for semiconductors, and you might want to go to Wikipedia and have a look at the definitive list, but it's enough to know that you can take a substance, in this case we're taking boron, and if you dope with boron, you create things that are called holes. Now, a hole is just a place where an electron wants to be. So we designate these as positive holes because they are a place that will attract an electron, which is negative. Okay, so boron is adding holes to our pure silicon. Please note that it may look like these holes are actually flowing in the semiconductor, but it's only because electrons are jumping through in this direction. These are actually located rigidly within the semiconductor. Now, you may be saying, well, how is that going to allow current to only flow in one direction? And we're not quite there yet. We need the next part of the equation. Incidentally, this type of doping is called p-type doping. Let's look at the next part of the story. So in the first instance, we started with pure silicon and we doped it with some boron. So we now have a p-type piece of silicon, which means that it has little spaces within its structure that will accommodate an electron. And those little spaces, like I said previously, are called holes. And they're holes that want an electron. Now over here, pure silicon, not a good conductor, but if we dope it with phosphorus or a number of other substances that are on the list in Wikipedia or wherever you go to look it up, we get free electrons. So unlike the holes, these free electrons that are created are able to flow around just like they would in a conductor. So we've now created a piece of silicon that will function quite well as a conductor, but like a conductor, it will allow current to flow in both directions. So you may, at this moment, have a big question mark in your head saying, well, how is that going to allow current to flow in both directions? Well, when we dope with phosphorus, we create a type of silicon that is called N-type. And this is a diode. When you have a p-type doped piece of silicon butted up against an n-type doped piece of silicon, we've now got ourselves our diode. Let's have a little think about how this works. So now we have a PN, and they call this a PN junction, because a junction is where two things meet. And our PN junction is now going to become a diode, or it's already become a diode. So instead of pure silicon, we have silicon that is doped using the doping agents we talked about previously. And one side, the P side, has the positive holes in its structure, and the other side has free electrons. Now, if I was to apply a negative voltage to this side and a positive voltage to this side, if this was a normal conductor, our conventional current would flow from right to left. But it's not going to flow in this instance, because have a look at what's happening here. We know that opposite charges attract. So if we put a positive here, our electrons are all going to want to go in this direction. So the electrons are the only thing that can carry current. They're going this way. And over here, we just have this giant void of silicon with holes in it. So the electrons are not able to flow in this direction, because you basically have this giant negative charge on this side that's saying, you cannot cross. You're not coming this way. But let's have a look at what happens when we put the polarity in the right direction and allow the diode to conduct. So now we're examining electron flow, and we will discuss conventional current flow in a moment. But electron flow is always opposite direction to conventional current flow. And when we have the polarity set up like we have it here, with the positive on the P, this is a kind of how I remember it, because positive equals P and negative equals N. What's going to happen is our electrons are going to see the positive over here. Negative loves positive, so our electrons are going to start flowing in this direction. Now, if this was pure silicon, they're not going to flow very well through this space, because, as we said, semiconductors in their pure state are pretty rubbish at being conductors. Because we've doped this with boron and made it a p-type semiconductor, it's got these beautiful holes, and the electrons love these holes, and they jump into the holes, and as they jump into the hole disappears, and the electrons will flow in this direction. So quite often when you talk about a semiconductor PN junction, they say that holes and electrons are flowing in the opposite direction when the thing is conducting. Now, that is true to an extent, but you need to remember that really what's flowing is the electrons. The holes look like they're flowing because as my electron jumps, say, from this hole into this one, it looks like the holes are moving in this direction. That's only going to happen on this side where you have the actual holes anyway, but it's something to remember about how this all operates. So that phrase, holes traveling in opposite direction to electrons, you just need to have that caveat in mind that the actual holes are stuck where they are. It's really the electrons that are moving. So the conventional current flow is in this direction, and the diode is now conducting. Swap polarities, diode stops conducting, put it around the way we have it here, the diode conducts. And so this PN junction has, as we said before, a schematic symbol that looks like that. So this is the equivalent of that. This side is the P side of the PN junction. This side is the P side of the PN junction. This is N, and our conventional current is flowing in this direction. When we polarize it correctly, positive on this side, negative on that side. Now, there is a thing called the barrier voltage, and you can go and look up how that all works. I'm not going to go into that depth of detail in this video, but if you are fascinated and you want to pursue it further, by all means, either in the comment section below, let me know whether you want me to discuss what barrier voltage is. The thing to remember basically is that when this thing is conducting, they say it is forward biased. And when it's got the voltages around the wrong way, it's called reverse biased. And the bias voltage for a diode is what you need to have across it to get it to start to conduct. So unlike a piece of wire, which might start conducting at millivolts, you actually need, for a silicon diode to be forward biased, you need 0.7 volts to get it to start to conduct. So that's often used, that voltage is often looked for if you're doing fault finding. So if I wanted to check to see whether this diode was conducting and whether it was okay, I could actually put positive here and negative here and just see whether I get a 0.7 volt voltage drop across it. So it's a really good way of fault finding as well. But basically what you need to know is that it will allow current to flow once we get to 0.7 volts positive on this side. If we reverse the polarity, it shouldn't let voltage flow until you get to hundreds and hundreds of volts, in which case usually the component has failed. Let's jump over on the test bench, build a real circuit, and have a look at how it works. Oh, enough of you. Get off my desk. Well, folks, as you can see in front of you, this is the brand new toy. It's a Handtech DSO2D15 digital storage oscilloscope. And it's got two channels. You can see both channels here. Channel 1 at the top here, which is, I think it's supposed to be yellow. I don't know if it's yellow on this screen. And green down the bottom. And you might be noticing that at the top here, we have a full sine wave. And the sine wave is at, it says it down here, 1.4 hertz. And it's 1.4 hertz at 5 volts peak to peak. So it goes up 2.5 volts, comes down to 0, and then goes down to minus 2.5 and back up to 0. And it's doing that about 1.4 times a second, hence the 1.4 hertz frequency. Now this signal that you're seeing fed in is actually being generated by the digital storage oscilloscope, because this DSO also has an arbitrary function waveform generator, a fancy way of saying a signal generator. It can generate various types of waveforms, triangular, square, and in this case, a sinusoidal sine wave waveform. So we have channel 1 coming out here, channel 2, and our waveform generator, which is generating the sinusoidal waveform at 1.4 hertz that you can see there. The waveform is going from 0 up to 2.5 volts positive, and then going back down to 0, and then going to minus 2.5. So it's 5 volts peak to peak, but it has a positive 2.5 volts and a negative 2.5 volts passing through 0. And as you can see there, at the top we have a full sine wave on channel 1, which is what is being generated by the signal generator. And at the bottom here, we're measuring the output after the diode. So I'll just show you that circuit, and we'll also flash up a little photograph of the circuit that we drop on the board and do a little bit of an explanation. And this is a prototyping breadboard. Now they call it a breadboard because back in the old days, people would often get a hunk of wood, like an old breadboard, and they would screw screws into it. and they would then put wires from screw to screw to prototype circuits, or even to build circuits for that matter. Quite often people would build transmitters on old pieces of timber. It's a lot of fun. And this is great for doing experiments and checking out circuits before you commit to actually building them. And as you can see here, we have feeding into this circuit our full sinusoidal waveform or sine wave. And then after this diode that we have here, I'm using an LED as our load. And you can see it flashing away there, and it's catching every half because we've really got two diodes in this circuit, but the load is just indicating when it's on and when it's off in this instance. So you can see there that it's flashing every half cycle, and that's what's shown on the output of the actual oscilloscope. So I'll just flash the circuit up. If you have a look at the circuit as it appears just up here, that's the circuit that you're presently looking at that's being created in real life on this prototyping board. And the inputs and outputs are what you're seeing on the scope. Let's go back to the scope again and do a quick recap. So as you can see on the scope, a full sine wave, that's what's coming in. And our diode is only allowing the positive voltages to produce a current. Whenever we go into negative realm, the diode is reverse biased. And as we said before, a reverse biased diode does not conduct current. Isn't electronics wonderful? Well, thanks for sticking around right to the end of the video. Welcome to Mission Control. I'm hoping that when I show people a little bit more about electronics, that it might head them in this direction. And what is this direction, you may ask? This direction is ham radio. And I know a lot of you younger people might think that it's a bunch of old guys talking about how much their prostate hurts and what they had for breakfast. And you will find those conversations happening on the air. But the great thing about ham radio, and the thing that probably unites a lot of us, although less and less of us as time goes by, is the technical aspects of the hobby. And if you get on the channel and jump on the ham playlist, you will find a whole lot of information about all the fun stuff that you can get up to once you get your license. So please let me know in the comments section below what electronic components you would like to find out more about, and I will do my due diligence on them and try and present a simple tutorial on the operation of a given component. Thanks for watching the video. 73, that's how us hams say best of luck, and I will see you in the next episode of The Art of Engineering.